In this module, we will discuss how to apply the root locus to controller design. In the previous module, we introduced a graphical tool called the root locus. And if you recall, the root locus plots all of the possible closed-loop pole locations as a parameter changes. Typically, this parameter is something like a proportional controller gain. We also presented a procedure for drawing the root locus and alluded to the fact that the root locus is helpful for higher order systems. So when we have simple canonical systems, first order, second order, we can just apply algebra to find the necessary gains to meet a specific specification. But for higher order systems, it's much more challenging, and the root locus allows us to see how multiple poles move around as we change a parameter. Specifically in this module, we will discuss how to apply the root locus to controller design. And so we're basically going to present a procedure and some examples. With our procedure, the first thing that we want to do is we want to translate our performance specifications into closed-loop pole locations. Things like settling time requirement, overshoot requirement, etc. Requirements on the transient performance of the system. We then will draw the root locus of the system with a simple proportional controller. Then we will use the root locus to try and identify whether or not there is a design of a proportional controller. Is there a value of the gain k that will meet our given requirements? If yes, then we're done. If not, then we need to try a more complicated controller, and specifically a dynamic controller, where we will add poles and or zeros to change the shape of the root locus so that it will pass through the region where we need the closed loop poles to be located. This may not be entirely clear, but as we go through some examples, hopefully it will become more clear. Let's now try an example to better illustrate the procedure from the previous slide. So in this example, we'd like to find the value of the gain k, where we have a negative feedback system with a simple proportional controller. So we want to find the gain k, if it exists, that provides this system, the closed loop system, a settling time of 4/3 seconds. Okay. So the very first step in our procedure is to translate the specifications into pole locations. So take a second and think about how a requirement on settling time translates to a pole location. Okay, so specifically, settling time is approximately equal to 4 divided by sigma, and we would like the settling time to be 4/3 seconds. So if we then solve this equation for sigma, we can bring the sigma to the right hand side. We can multiply through by the 3 and divide through by the 4, and then we get that sigma is equal to 3. Okay. And so from a first glance, we can right away see that we're not going to have a canonical second order system, because we're going to end up with a 0 in our closed loop system. Despite the fact that this won't be a canonical second order system and this relationship won't hold exactly, the root locus will still be helpful to us as a way to help us know how to tune the gains. The second step in our procedure is to draw the root locus with this simple proportional gain. And so this is something that we did in the previous module. If you recall, you can go back and look at how we did that. So this is the root locus. These lines show all the possible pole locations as we vary the value of k. So when we start with k equals 0, the closed loop poles are located in the same location as the open loop poles, and as we increase k, the closed loop poles move along these branches. Eventually, if we increase k enough, the system goes from being underdamped to overdamped. the closed loop poles go from being complex to being real. That occurs at this break-in point, and then the poles keep going, and the closed loop poles, one of them approaches an open loop pole, and the other one follows along an asymptote that we can think of as a zero at infinity. When we draw the root locus, we also need to include the pole locations corresponding to our specification. So on the previous slide, we found that we wanted sigma to equal 3. And so take a second and think about what pole locations correspond to a sigma equal to 3. Okay, if you recall, sigma is the real part of a pole. So sigma equal to 3 means that our closed loop poles have a real part of -3. This is negative sigma equals -3. So all poles that are on that line will have a sigma equal to 3. Now the question is, can this requirement be met? Is there a value of k? Is there a proportional controller which will give us a sigma equal to 3? So take a second and think about this. So it turns out that the answer is yes. And the answer is yes because there is a portion of the root locus that crosses this dotted line. So there are values of k where we can place the closed loop poles on this dashed line, where this dashed line corresponds to poles with sigma equal to 3. If we wanted to find the specific value of k, one thing that you could do is you could go back to the ultimate requirement of, you can go back to the condition based on which we drew the root locus. And so in this case, this closed loop pole, it has a real part of -3. We don't necessarily know what the imaginary part is, but we know that it has a real part of -3 and it has some imaginary part we could call omega. And so what you could do is you could substitute this value of s into this equation and find a value of k and a value of omega, which will make the two sides of the equation equal. In this class, we won't really do that. Instead, we'll use MATLAB. So this figure was drawn with MATLAB, and from MATLAB we can find the value of k that puts the closed loop poles exactly at this location. So we will use MATLAB to find k. Looking back on the previous slide, we saw that this system will not be canonical. So in fact, it's likely that because of the presence of that 0, that the settling time won't be 4/3 seconds. It could be smaller, it could be larger. That being said, this root locus is still helpful because we can see how change in k moves the closed loop poles. So if we find that our settling time is too large, we can make the settling time smaller by moving the closed loop poles to the left in the complex plane. Moving the poles to the left makes sigma larger, which makes settling time smaller. So recall, settling time is 4 divided by sigma. So if we make sigma larger, we make settling time smaller. So even though we may not have a canonical system, the root locus can still be helpful. If we keep increasing k, then these closed loop poles will keep moving, this one down, this one up, until they hit the break-in, and then one branch will go to the right and one branch will go to the left. And it turns out we could pick another value of k, a value of k larger than the one that placed the poles here at these squares, we can increase the value of k and we can get a pole that also has a real part of -3 for this value of k. So take a second and think about whether or not that value of k would meet our requirements. So in this instance, we'll have one pole with a real part of -3, but we'll have another pole that has a real part that's not -3. However, if you recall that the slower pole dominates, this pole is slower. The pole with the smaller real part is slower. So this pole will dominate. So even though we have two poles where only one of them has the sigma we desire, this pole is faster, and so its contribution will be less, and this pole will dominate. So again, we may not have a settling time of exactly 4/3, but it will likely be close to 4/3 because this is the dominant pole. So this is another example of how using the root locus can be helpful for controller design.